was there, and they had a deal where they had software that took my computer screen, and then they had a separate camera on me, and it imposed me on top of the PowerPoint thing. It was really slick, but we're not quite there. We're not there yet. So, do we have a quorum here? Should I start talking? Okay, so what I'm going to do is give you a little short lecture that's just an overview of what's going to happen in the next 4 weeks and how the class is organized, viewed from 3 or 4 different ways you could think about what all is going on in the class. So, as Emmanuel said, in general, we'll have lectures in the morning and labs in the afternoon. But there's a lot of variance in this. If it's, the weather forecast is cloudy in the afternoon, maybe we'll go out in the morning and make the measurements and then have the lecture in the afternoon when the thunderstorm's going on. We'll just play that by ear, and especially towards the end of the course, we may change things around because you decide you need another day to do whatever, we'll fit things in. So we will, at least as needed to start, maybe the first Saturday, we'll use Saturday mornings to tie up any loose ends and kind of, take a view back at the week and see what was missed and what worked and what didn't work. And then Saturday afternoons, you'll have free. You can party. You'll probably want to catch up on sleep. You may want to go around the coast of Maine here. There's some pretty neat things to see. Past classes, students have gone to Acadia National Park. Just at the end of the peninsula we're on is the lighthouse that's on the back of the main state corridor. So you definitely need to get down there. And they have at least a couple of kayaks. You can go out and piddle around here, and you'll find out I'm the kayaking expert of the class here, as is Emmanuel. So anyway, I often try to go out and do a little paddling. When the tide is right, sometimes I paddle up to Damariscotta for lunch and then ride the tide back, or you can go south, depends on the tides. And the tides here are about 3 meters to 4 meters, so they're pretty substantial. Okay, so the way the class is put together, one viewpoint, kind of chronological and by topics, is that you're going to have to figure out how to describe the optical properties of water, phytoplankton, dissolved substances, mineral particles, air bubbles, all the stuff that's in the ocean. And those are what are called inherent optical properties. They're the absorbing and scattering properties of these different components that are in the ocean. So the first week is basically learning about how you measure absorption and scattering by all these different things that are in the ocean. And so that's, introductions of a lot of basic concepts, and it's the basis of understanding how light interacts with matter. And you can see here's a bunch of different phytoplankton in here. They look totally different. That's because those phytoplankton have different absorption and scattering properties. So that's what we're going to concentrate on the first week. So in the afternoon labs, the measurements you're going to be learning how to do are how to measure absorption by dissolved substances. So you use spectrophotometers. There's instruments called AC9s and ACSs. You'll use those. You have to learn about measuring absorption by particles and also scattering by particles using these various instruments that we'll have. And then I think on Friday there's also a lab on learning how to run software that does what are called me calculations, which is a way of computing what these absorption and scattering properties are if you give me the properties of a particle. So you'll learn, Emmanuel will have a lecture on that, then you'll have a lab on actually doing these calculations. So then the second week, we've now learned how to describe the optical properties of the stuff that's in the water. Now we have to figure out how to describe the light itself. So that's a little field called radiometry. And so we'll have some lectures on that. You'll start making measurements of the wavelength dependence of different measurements of the light and so on. And Ken Voss will be running a lot of those measurements. And then this business of radiometry, which is the fancy word for, studying light, that leads us into something called apparent optical properties, or AOPs. And one of those is what's called remote sensing reflectance. So that leads us into the whole business of remote sensing. So the second week we concentrate on measuring light and the properties of light, and then these other things that you can get that describe light in one way or another. We'll have a lecture on a thing called the radiative transfer equation, and we'll get started on remote sensing. Then the third week, the week 2 in the labs will also, you'll be measuring these above water and in water radiances, irradiances, photosynthetically available radiation, et cetera, different instruments there. We'll have some labs on measuring fluorescence by chlorophyll and CDOM, and also Raman scatter by the water. You're going to have to learn how to calibrate these sensors, talk about measuring particle size distributions, which strongly affect the scattering by light. And then there will also be a lab by Colin on how you take, for example, this remote sensing reflectance and go backwards to get the inherent optical properties of the particles that are in the water. So that's what happens in week 2. Then week 3, this is the really fun week. So how many people here have never been seasick? Okay, this is your opportunity. Do not pass it up. We'll try to find a rough day for you. Anyway, we will now go, you now know how to measure the particle properties and so forth. You know how to measure the light properties. Now you're going to go to sea and do it all together. So we have a research vessel here, the IRC, and as Emmanuel said, we'll split into 2 groups, and one day half of you will go out on the IRC, get all kinds of measurements. The other half will stay in the lab, and you'll learn how to run this software called Hydrolite that computes all these optical properties. And then we'll also get into the business of atmospheric correction and vicarious calibration. That's when Jeremy Wardell from NASA shows up, and he's the god of that business there. So you'll see how all of that works. So we're getting more into remote sensing. And then in week 4, we kind of bring it all together. We'll have some miscellaneous lectures on like kind of the odds and ends that didn't quite fit into the first 2 weeks, things like color and Monte Carlo simulations and so on. So they're things you need to know, but they're not what you have to know right at the start. We'll have a couple people come and give some guest lectures, and then we'll also have a couple of lectures on the non-hard science things like ethics and science. How do you market yourself when you have to get out of here and start writing proposals? What are your different options for careers? The back row is largely academics. I've never been an academician. I've always worked for private industry or for the Navy, something like that. So it all works out. You'll, along the way, come up with some little student project where you want to look at some particular thing, or you want to learn how to model a particular thing, whatever. You'll figure that out over the next couple of weeks, and you'll have some time to work on your student projects. And then the last day of class, each of you will get up and give like a 15 or 20 minute presentation of your student project, whatever it turns out to be.
And those can be done in small groups.
Yeah. And then like Emmanuel said, you guys, we're all working together here. So it may be that 2 or 3 of you get together and work on some one particular thing, or maybe you just want to be an individual and go do more modeling of whatever. That's fine. Doesn't really matter. Another way to look at everything that we're going to do in the class is think about sort of the life of sunlight. So there's all kinds of things that can happen to sunlight as it comes through the atmosphere and interacts with the ocean. And we're going to look at all those different pieces. So, for example, some of the sunlight, it comes in, maybe gets absorbed by the atmosphere, like by ozone. It might get scattered by non-absorbing molecules, and maybe it goes up to your satellite. Some of it might be scattered by aerosols, which are little particles, can be water droplets or dust particles. So some of it's scattered by that. Some of this light will reflect off the sea surface. Some of it actually gets into the ocean, and what gets into the ocean, it might be absorbed by phytoplankton. It might be absorbed and then re-emitted at a different wavelength. That's fluorescence by chlorophyll or CDOM. It can bounce off of phytoplankton. It can be rescattered by water molecules, maybe at the same wavelength, maybe at a different wavelength. And some of this light gets out of the ocean and will eventually get back up to an aircraft or satellite. So of that light, that's detected, say, by the satellite, well, what do you do with those measurements? Well, they get downloaded to a ground station. They get sent off to the NASA Ocean Biology and Processing Group, which is Jeremy Wardell in particular. He'll be down here. He's going to talk about all of this part of the calculation here, and you have to correct for this light going through the atmosphere, which messes it up, because what we're really interested in the water, not the atmosphere. So this is noise to us, and this is signal. If you're an atmospheric person, this is signal, and this is noise. But anyway, Jeremy will go through all this business of atmospheric correction, and you'll learn how do you go to the NASA data websites and actually download imagery, download chlorophyll maps, et cetera, and finally you come up with a map of something like that. So that's another way of thinking about all the little pieces we're going to talk about during the class. Another way to talk about it is this organization chart, which is on the wall over there. But I've grouped things here where here's all the inherent optical properties. So absorption, a thing called the volume scattering function, scattering coefficients, beam attenuation, et cetera. So that's all the properties of the medium. And you can see we've got a bunch of lectures starting with Colin today. Lectures 2 and 3 are going to kind of give you an overview of light in the ocean in lecture 2. And then lecture 3, she's going to talk about this box right here, the absorption coefficient. And then there's boundary conditions, which means what's happening at the sea surface or the sea bottom. There are internal sources, which are these fluorescence, Raman scatter, et cetera. We'll have some lectures on those things. All of this stuff here goes into what's called the radiative transfer equation. So I'll have a lecture on that. We'll have a big lab on the Hydrolite software solves this equation and puts out radiance. And then from radiance, you can derive everything below that. So there's all these irradiances. I have several lectures on the red box here. And then down here are all these reflectances and so forth that are the basis of remote sensing. And you can see there's a half a dozen lectures that are going to be about the stuff that goes on inside that box. So that kind of brings the whole field of ocean optics together, and we'll just keep going back and saying, okay, I'm doing lecture 7 now. That's this box right here. You can kind of see what all's happening. So kind of the promise of the class, 4 weeks is not going to make you an expert, but it's going to give you a good introduction. And so by the end of the class, you should know the basic vocabulary, and understand the basic concepts, all this absorption and scattering and radiance versus irradiance and remote sensing reflectance and all that kind of stuff. So you can then go out and read the literature and understand what they're talking about. You'll be, at least halfway comfortable with operating, a dozen different kinds of instruments. And, I love to play with instruments, but they never let me go to sea because I'm branded as a theoretician, and so they don't trust me with instruments, but they're still fun to play with. And you'll get probably be much more expert than I am at actually making measurements. And you'll learn how to download ocean color imagery from NASA. And also nowadays, if you get funded by NASA to go to sea and make measurements, after you've got your data cleaned up, you have to upload your data to the NASA archives where they store everybody's data. So you'll learn how to upload your data and then download the stuff that Jeremy Wardell creates. You'll learn how to run this Hydrolite software, Me codes, Monte Carlo codes, and so forth to actually do various kinds of calculations. So that's it. So basically by the end of the class, you're going to learn to speak the language of optical oceanography. And you're going to learn how to make various kinds of measurements of absorption and scattering and so on. You'll learn how to measure light and how that fits into everything. You'll learn how to run the Hydrolite software, which computes the light fields. and you'll learn how to collect field data and piece that all together. You'll learn how to analyze the data. That's, the numbers that come out of the instruments are not necessarily any good. You've got to do a lot of smoothing and correcting and throwing out the bad data and correcting for this and counting for that. So you'll learn how to do that in the labs, and you'll learn how to relate the optical measurements to the physics and biology of what's going on in the water. You'll learn how to obtain the NASA imagery. You'll learn how to take that imagery and basically work backwards to figure out what's going on in the ocean. That's the whole business of remote sensing. You'll learn how to upload your data to this CBAS NASA data archive system. You'll at least get a feeling for what goes into designing a field campaign and all the things you have to think about before you get on board the ship, and what are you going to measure, and how's it all going to fit together with everything else. And the world is full of data sets where they went out and they measured 4 things, and then they got back and realized, oh, this 5th thing I didn't measure, but that's what I really need to know. And so therefore my other 4 things are not all that useful. And then finally, you will just learn how to be an optical oceanographer as opposed to a physical or geological or some other kind of oceanographer. So that's what the class is all about. And hopefully by the end of it, you'll feel like you got your money's worth here. So that's it for this little introduction. I guess I'll just turn it over to Colin now, unless we need another bathroom break. And I should also comment, everybody has different learning styles. I'm the kind of guy that likes to just have this very formal lecture where you start out with definition number 1 and go from there. Other people are very hands-on learners, so you may have, or you will have, like a lecture from me on radiometry. It's going to be the theoretician's way of doing things. And right after that, Ken Voss is going to give you a lecture on radiometry, and it's the experimentalist way of doing things. And between the two of us, maybe you'll sort of figure it out. But anyway. Beg your pardon?
Paying a lot of attention to your lecture.
Oh, yeah, okay. Oh, let's see.
I have to do that.
We wish to have your golden voice preserved for posterity.
Sad.
Okay, there's that. You can clip that on somewhere and you're good to go.
Try not to strangle myself. All right. Okay. So I will never give you my lecture ahead of time. The reason is because I pose a lot of questions in my lecture, and I don't want you looking ahead to see what the answers are. So, but I will give you my lectures afterwards. Does that work? Okay. Okay. Well, I'm Colin. I work in the Department of Earth and Oceanographic Science at Bowdoin College. We have a number of students in the class who were my former students. I'll leave you to figure out who that is. Let's see. Okay. So I'd like to follow up with what Curt was just saying in thinking about the fact that we have, among all of the instructors, people with a lot of diverse background. I actually came to oceanography from marine biology and geology. And that's what I got my undergraduate degree in. And then I got a master's in physical oceanography and a PhD in biological oceanography. And then I did my postdoc in optical oceanography. So kind of I did everything but chemistry. So I think after that, I've learned to really appreciate chemistry. So I kind of feel I'm a well-rounded person. As Curt said, we have a lot of different teaching styles, and I'd like to think about that a little bit more. We'll get into that. We also have a lot of different backgrounds of students in your preparation. And so there will be very diverse learning styles actually within each person and between each of you. So I want you to think about what kind of learner are you? Do you learn best when you read something and you can take notes and you can go back to it? Are you a person who likes to hear someone else talk about it because it clarifies it for you? Do you like to have a discussion with your classmates or with your professors or both to try to really kind of get to the nitty-gritty? Are you someone who likes graphs? I'm a person who likes graphs. That's how I figure things out. I usually have to graph things up. I have to take an equation and I have to graph it. I have to take some data and I have to graph it. And once I graph it and I think about the different ways of presenting that data, I'm like, I get it now, right? Are you a person who likes to look at equations and be able to manipulate them around and figure out how one thing is related to another? Do you like hands-on activities? Doing it and then figuring it out? Are you a little bit of everything? So I'm actually going to write these things on the board after break or during break. And I want you to casually go by and put a tick mark of what kind of a learner you think you are. Okay? And as we go through the lectures and go through the labs, think about which aspect kind of spoke to you. And I'll ask you as we go through these weeks, like, what thing worked for you? We talked about absorption 5 different ways. Which one gave you that, like, oh, right, I get it now? Because it's really important to know what kind of a learner you are and to think about, how you access information. So we'll spend some time thinking about that. Some of the strategies that we're going to use in terms of learning, in some aspects, you will be an independent learner. And one of the things I like to use is something called a knowledge survey. And so I might pass one of these out, or I might have Sasha post it and have you do it before you come in. A knowledge survey is where I ask you some questions, like, what's the volume scattering function? And you don't have to answer it. You just have to say, I'm pretty sure I know what that is. Or, I've never heard of that. And it's interesting because your response to the question of how confident you are in your answer actually really helps instructors understand where we need to come in and teach. And so I use it as a guide for myself. And then often what I do is I give you the knowledge survey after the lecture, and hopefully you're just a little bit more confident. That's my goal. If you're not, then that means that I didn't do my job. We also have a lot of collaborative strategies. So one of the ones that I will be using in class is something called Think, Pair, Share. Has anyone ever heard of Think, Pair, Share? Yes, a couple, 1, 2 people. Okay. So what it is I give you a question or a problem, and I want you to consider it a little bit on your own. I want you to think about, oh gosh, what does she mean? I want you to brainstorm a little bit. And then I'll say, pair up. And you'll go to the person next to you or the person behind you, and you guys will start to discuss what you think the answer to the problem is. And maybe you'll get a little bit more insight when you put your 2 heads together. And then you're going to share your information, work through the questions, and see if you can articulate what you think the answer is. Sometimes we think we know the answer, and then as soon as we start telling the person next to us, you're like, whoa, wait a second. Maybe I don't really know what the answer to that is. And that's a really good way to figure out where your limits are. The other thing that we use in this class is called a jigsaw approach. Anyone heard of the jigsaw approach? It's my favorite. What is it, Jesse?
It's where everyone is kind of broken up into groups before, and each group is in charge of learning one thing by themselves, and then you come together, and one person from each group comes together. So you have like A, B, C, D come together if you had A separate before, and then they teach each other.
Exactly. And so in fact, we're going to be doing this in the lab tomorrow. We're making a bunch of different measurements in the lab. We have a bunch of different water. We have a bunch of different types of samples that we're going to filter and look at. And in the old days, we used to have every person measure every sample, analyze every data set, and then come together and talk about it. which is great if we had 2 months. But instead what we do is we have you measure one water, you measure a different water, and you measure a third water. And then you bring your data sets together. You each analyze the data, bring it together, and then you have the full experiment. So that's a jigsaw approach. Okay? It's really a wonderful way to do science. It's the way collaborative research is done as well. We don't all do everything. So this is a good model for research. And then finally, assessment. We don't have exams in here. So, but I am going to employ something called an exit slip. And I'll set up a little box after our lectures or at the end of the day. And that is where you can just like write down a little something that maybe you learned today. Something that was different from what you knew before. And also it's a great place to put in those nagging questions that we just haven't answered yet. Or maybe I didn't quite get that. And that will be really helpful to us so that we could go back and just make sure that everybody is moving up. And then finally, the group presentations. And so this is where you display your accountability for the work that you've done in this class. And we do this in the mornings. So you will do lab in the afternoon. You guys will do a bunch of analysis. You'll prepare a little presentation to show to us that you know what you're doing based upon our labs. And then it's an opportunity for all of us in the back to say, hey, wait, did you think about the temperature correction? What was your, how did you average your data? And so it's a way for us to assess what you've done, give you the opportunity to revise it, and resubmit if you want to make sure that you can get to the right answer. That's about as far with assessment as we're going to go. Okay? Any questions on that? Nope. Cool. Okay, this is one of my favorite pictures. I have to turn off the lights for this so you can really see it. Right? It's so beautiful. Okay. Enough of that. I'll return to it. Curt showed this really great diagram that's from his book, and where he talks about the inherent optical properties, environmental boundary, or conditions and boundary conditions, how those feed into the radiative transfer equation to get to radiometric quantities, measurements of light, and how we use those measurements of light to derive some other properties of the ocean that are apparent. We'll talk about each one of these. So we call this the forward problem, and Curt alluded to that if we knew what was in the ocean, we could predict some of the measurements that we make from satellite. And so there's a really nice diagram from Born and Huffman called discerning forward models and inverse models. So in the forward model, if you knew the dragon, you could predict what its tracks were, right? That's the forward model. So Daenerys clearly knows what kind of tracks her dragon is going to make. I did not see the final season, so please don't tell me anything. I can't watch it. My kids are 14, and they just should not watch it. And I can never be in a room where there's some sort of screen that they are not. So don't ruin this for me. Okay. Then there's the inverse model. If we managed to find tracks of a dragon, could we figure out what dragon it was? Right? So it's sort of like, here's the egg. Does she know what dragon that's going to be? Is it going to be this cute little one that sits on her shoulder? Or is it going to be this one? Right? We don't know. But if we knew something about the tracks and how they could predict the size or the shape or the color of the dragon, then that would be the inverse problem. Okay. So, the inverse problem. So now we're going backwards. Okay. So let's trace sunlight from the sun and into the ocean. Here's one of my new favorite pictures of the sun. This is taken from the space station. You can see the Earth underneath in the camera. So this is always a trick question that I have for my students. What color is the sun?
All the colors.
It's all the colors. Who said white? White. How do you know that?
Because it has all of the wavelengths.
How do we know it has all the wavelengths?
split it and see them all.
Beautiful. You didn't look at the sun, right? Because I always get students say, well, you just look at it and it's white. And then I say, don't look at the sun, it's bad for your eyes. Okay. Yes, it is white. So it turns out that we can model the sun really well if we treat it as a black body. And so black body radiation says that any object that has a temperature above 0 is going to emit electromagnetic radiation. Okay? And it turns out that the hotter the object is, the more energy it's going to emit. And it turns out it's not linear. It emits more energy proportional to the temperature to the 4th power, right? And it also turns out that the hotter that the object is, the shorter the wavelength of its peak emission. So the hotter it is, the bluer it is. So I'll get to that in just a second. But Planck's law is the law that has an equation that describes the spectrum of emission from a black body, depending upon its temperature. And it's kind of in a complex way. This is the equation. You guys have probably seen it before. And it gives you this nice curve. Now, the shape of all these curves, these all differ. This is the emission, and this is wavelength. And each one of these is a different temperature. So the shapes of those curves are all identical. It's just the magnitudes are different. And there's a shift in the wavelength. So the hotter black body can emit here in the blue, ultraviolet. And this is a black body that's about 6,000 degrees Kelvin. It's in the green, and it shifts longer and longer. Now, the sun's about 5,700 degrees, so it's a maximum emissions in the green. So I teach in a department that has a lot of geology classes. And one of the things that we learn is the temperature of the core of the Earth. Does anyone know the temperature of Earth's core? It's about 7,500 degrees Kelvin, which is hotter than the sun. So what color is the core? Yeah, it's like purple blue. So we always show it as red, like the red hot iron core, but it's not. It's purple. So anyway, okay. So you can model this. This is just a model of the emission by the sun once we can get it, away from the sun and to the top of the atmosphere. And this is the visible portion of that emission. And so if you blow that up, it looks like it's basically a little bit of all colors, right? We have almost equal energy across the spectrum. Yeah, there's the spectrum. Okay, well, as much as I can do in like PowerPoint animation. So if I took a measurement, I was out with one of my classes, and this is the spectrum that we measured. And you can model, so this is top of the atmosphere, and this is top of the boat. And there's a difference, right? So what's the difference? Different magnitude, different shape. Atmosphere, right? We've got a lot of different features here which represent some absorption. We've definitely got attenuation overall. And that is because of the atmosphere, which is another one of my favorite pictures. Okay, let's take a minute to look in awe at the atmosphere. Again, taken from the space station. What can you tell me about the atmosphere? It is so thin. It is so thin, and it is so important and vital to this planet. And we should stop messing it up, right? There's not much there. What else can we say about it? It's what? Mostly nitrogen, yeah. I mean, we can't tell that from this unless you can do spectral analysis with your eye, which maybe you can. It is mostly nitrogen, like 70% nitrogen. What else can you see from this? Yeah, it's got this beautiful blue color. Especially at the top, you can resolve it. It's varying in its optical thickness as well. Right, so there's just so much that we could begin to, so many questions we could begin to answer with just this image about the atmosphere. Right, and the sun certainly doesn't look white here. We've got this beautiful reddish corona. So, lots of beauty. Okay, so if we look at the spectrum of radiance, which you'll learn the definition, but it's essentially the amount of energy, the watts per meter squared per nanometer, because we're resolving it on nanometer scales here. So this is top of the atmosphere. This is what happens when we get to the surface. Again, we have all of these different features that are absorption by gas. And this is what it looks like about 10 meters below the ocean surface. So we can see an overall attenuation in the atmosphere and then a very strong attenuation in the red once we get into the water. And so we'll talk a lot about what that is. But essentially we have water itself, and particularly the dissolved matter, that is taking care of all of this light here. Okay, so let's imagine we're on a planet that doesn't have an atmosphere. So we're just going to have a sun over here. And this is the ocean. There's no land either, because that would be a perfect world, right? Waterworld. Well, Waterworld was a terrible movie, but the idea of an ocean world, I think, would be great. My kid just did a science fair at school. It was just with their class, and they had to do all this really interesting, like, make a planet in a solar system. And there was one kid who had a planet that had no ocean. And I was just like heartbroken. She was like, well, there's some lakes there. It's like, no, ocean, are you kidding? Okay, so color is the sun. We figured out the sun is white. What color is the sky going to be if we have no atmosphere? Why? Because that's what the universe looks like, right? There's no scattering, right? That would be so cool. So we used to do these models with Howard Gordon. We'd call it the Howard Gordon atmosphere, because he would model a solar beam in the absence of an atmosphere, and you would just imagine, like, it would just be like outer space. It'd be very cool. Okay, so I would like you to, for this scenario, just sketch what you think the angular distribution of the light is on the ocean coming from this sun. Remember, the sun is very, very far away. Go ahead, sketch it. Yeah. Sketch the ray path, or what the light is going to look like. So if I were going to measure it, or even sit in it, what would it look like? Okay, everyone have a semi-perfect sketch? Okay, so color of the sun, white. So I'm going to change all my diagrams to this from now on, a white sun. What color is the sky? We determined that it was black because of lack of scattering. Okay, so now we're in this world. And then the angular distribution of the light. What does everyone think? You drew a sphere. So a sphere like this? Yeah. So those would be like wave fronts coming in. Okay. Anyone draw anything else?
Would it just be straight lines? Is there no scattering?
As if there was no scattering. So just straight lines coming in, each representing maybe a stream of energy, right? Or the direction of propagation of the waves. Anyone have anything else? Yeah? Perpendicular to the ocean coming down straight. Okay, so even over here, coming down straight. Okay. So here's what I drew. I drew this, because my assumption was the sun was over here. But you were right also, because you can draw the energy being emitted out of a sphere as propagating wave fronts. So that is also correct. Okay, so there we get to the different learning, right? Different ways of expressing things, both of which are right, all of which are right. Your sun was just overhead, right? I don't think while we're here we're going to get the sun directly overhead, but that's okay. All right, excellent. Okay, so now we've got an atmosphere, and I want you to answer the same questions. So, what is the color of the sun? It's still white. Is it? Okay. I don't know. I said redshifted. What's the color of the sky? Blue. The sky is blue. Why is it blue? Or how do we know it's blue? Well. And why? Pardon? Rayleigh scattering. What is Rayleigh scattering? Very small particles. Very small particles in the atmosphere do what? They will preferentially scatter shorter wavelengths, which are bluer wavelengths. And so the solar beam of the sun now becomes depleted in the blue photons, hence the reason why it's a little bit redshifted. And the sky becomes blue. Okay? All right. So now, sketch the angular distribution of the incident light. You can add it to your other drawing if that's helpful, or you can do a new drawing, or you can use the same drawing, or you could pull out a pack of colored pencils. Who is super confident that they know what the answer is? Who is a little bit confident? Who is somewhat confident? You don't have to raise your hand. So, sometimes the thing that we see every single day, we don't think about that much. We take it for granted, right? So, we have this blue sky, and we still have this solar beam, right? We still have the solar beam coming in. But this blue sky represents light traveling in all directions, right? There'll be some angular distribution to it, and we'll spend a lot of time with Curt and with Ken thinking about the angular distribution of light in the atmosphere, but it's not all going to be coming in like this, right? And in fact, in one of the radiometry labs where you can measure the light that's incident on the ocean, you can block the sun with a disk and measure the distribution of light not coming in from that angle. And you can measure the color of it. And it's really different. In fact, if you measure with a radiometer, a spectroradiometer, at different times of the day, you can begin to, as the sun gets lower and lower in the sky, you will essentially be measuring the sky light. Okay. And so thinking about that will make you look at the sky in a totally different way than maybe you did 10 minutes ago. Okay. All right, so the atmosphere reduces the intensity, changes the color, changes the angular distribution, makes it interesting. So we'll be making measurements, I think in lab, I can't even remember which lab it is, next week. Doing a lot of stuff. And you can kind of think about what leads to natural variations in the intensity and the color, and then what happens when you're trying to make measurements. And Ken will talk an awful lot about making measurements of radiometric measurements. Okay. Clouds do what? They absorb and scatter and transmit. Yeah, all those things. So they change the intensity, the color, the angular distribution, but just in a different way than the atmosphere does. And they also have a huge impact on remote sensing, depending upon what wavelength you're interested in. So we have this cartoon called Calvin and Hobbes. He doesn't write it anymore, but it is very, very funny. I encourage you. Calvin's kind of a bratty little kid. His dad's kind of clueless. Hey, Dad, what are clouds made of? Oh, I don't know. I think they're mostly water. Well, how come they float? Well, it's sort of evaporated water. Maybe there might be other gases. I don't know. I'm not too sure. Well, then why are they white if the rest of the sky is blue? And you guys are going to totally know the answer to that question if you don't know already. Well, heck, it beats me. I guess we should look this stuff up or come to an optics class. I guess there's no qualifying exam to be a dad, but there is one to be a graduate student. How many people have taken their quals? Yeah, me too. Yeah. Okay, so now we're at the ocean surface. We're going to look at surface effects. Kurt's going to talk about this. My son's way over here now. Okay, so we have this incident beam here, and what happens to it? You already sketched it. I saw you. Tell me your name again. Alejandra, yes. What happens once it hits? Strikes the surface and, yes, transmitted and scattered. So we have some reflected and we have some transmitted, right? Excellent. And then we want to think to ourselves, I want to show this really cool image. So this is just a crazy image. So this is in Abasasta, India. It's a little atoll in the Indian Ocean. And it has this crazy appearance. This is what it looks like, actually, from an airplane. But the reason why it looks like this is because of reflection off the surface, called specular reflection. It gives this really weird, whitish, mirrored appearance. And it's different in the lagoon and outside the lagoon. So surface reflectance is really crazy looking. Okay, so of the light that is transmitted across the interface, what is going to affect that light? Particles are going to do what? They're going to scatter the light. What else? Phytoplankton, did you? Phytoplankton absorb. Thank you, 3 for working together on that. Anything else? Water. Inorganic sediment. Dissolved organic matter. Detritus. Bubbles. I don't think I had that on my slide. Dang it. Okay. And those are all going to absorb and scatter. Phytoplankton might fluoresce. Sea dum might fluoresce. There might be some bioluminescence. All of the material in the ocean is going to impact that beam of light in different ways. So absorption, scattering, re-emission. Okay, so we have another case study here. Let's think about an ocean that has no particles in it. And what I mean by no particles, I also mean there's just no scattering. Not even scattering, not even molecular scattering. There's just no scattering. It's just an absorbing ocean, okay? So I want you to work with the person next to you, and I want you to discuss what you think. We're in this beautiful boat. This is a beautiful boat. This almost looks like the Irish Sea, which we're going to be going out on. You can almost see a manual on deck. Ahoy! What is it going to look like when we are on this boat looking over the side? And if you're a diver, what is it going to look like? Okay, sun's up there. Okay, take a minute. You can go in groups of 3 too if you don't have someone right next to you. There is no scattering. We're ignoring molecular scattering. There's no reflection. We are looking solely at this beam that has come down. So there's no, we're going to ignore reflection off the interface, and we're going to ignore scattering in the water. It's a theoretical ocean.
So if you look at from surface, like above what it was, black, and then if you enter, you see that could be not there.
Okay, what do you think? What are we going to see when we look over the side of the boat?
Black.
Black. How many people say black? Anyone not say black? Awesome. Why? All the what?
All the light is gone, it's all been absorbed or something, it's nothing.
Yeah. There's nothing to redirect it back up. It's okay, Jessie. It'll still be a beautiful ocean. She's got a sad face. Okay. What are the divers going to see?
That's a good point.
Well, we could just assume it's the sun. So as you're in the water, say you're near the surface, what's it going to look like?
A little bit blue shifted.
Because of?
Absorption factor water.
So I didn't tell you what the absorption was, but yes, the absorption by water, it does. It absorbs most of the red, right? So it's shifting the light to the blue. And what if you go a little bit deeper?
Black.
Yeah, ultimately, it's going to go blue, 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 and then to the point where it's totally absorbed, right? So we will still have euphotic zone. We will still have happy phytoplankton. It's just that we won't get to see it. Okay. Be terrible for remote sensing. Okay, so is there a natural analog that you can think of? Or did I just totally make up this crazy idea?
Someplace with a lot of sedum.
Yeah, right. So, maybe the Rio Negro. What'd you say? Bisky Pond, a place that you should go swimming. It's like, 20 minutes from here? It's a beautiful place to go swimming. Also, the Rio Negro. This is in the Amazon, and it joins this other river here, and now I can't remember which one it is, the Salamoas. And you can actually see the two joining. And if we go up close, it looks like this. You've probably seen this picture. So these are two very different rivers coming together, right? This is a black river, and this is a white river. So this one has lots of dissolved organic matter, and this one has lots of sediment. So this one's very bright, and this one's very dark. Okay. Love this image. This is what happens when you get up close. Okay, so now let's think about an ocean that has no absorption, even water, no water absorption. Heading you off at the pass. But it does have particles. So welcome. So now I want you to think about, take a minute, what is this going to look like? Ready, go. Work with your partner. All scattering. You can ignore the atmosphere. Just think about the sun. Solar beam. Are you going to explain to her what you guys are doing? Cool. hard. You guys good? Think you got it? All right, let's group up. What does the ocean look like from the boat? White. Why? Because what? It's all scattering. Yeah.
But like different things in the water are scattering differently. So would it be
Exactly.
white?
So what if you have small particles and big particles? Well, we have to think about the directionality of scattering, but if all you have is scattering, that's the only thing that can happen. So there's no shifting of the color because there's no absorption. Okay? So we'd have to think a little bit more carefully about the directionality and what would happen. But what if you were in the water?
It depends on the depth.
Yeah. Does it?
Well, there's no sun, it'll still be black. No light.
No, there's sun.
I think it's
But if you go down deep enough, it would still be black.
Why?
Oh, maybe not.
Right?
Yeah. It's not controlled, right?
If it's not absorbed, it's like being inside an integrating sphere, which we're going to do in the lab. Ooh, be like being in snow, right? Okay, so what's our analog? We'll get to that answer. That has elements of rightness.
Lots of mineral particles
Lots of mineral particles. Huh?
and less plankton.
Yes. Things that don't absorb but scatter, right? What were you going to say?
Yeah, high resuspension, one of the systems that can be really bright.
Excellent. Any other ideas?
Maybe like a super saturated chemical.
Like formazine,
Yeah.
which we use as a standard for scattering, which doesn't absorb. Yeah. I thought of snow and ice as being kind of an analog. Okay. This is the Aurora Australis plowing through sea ice in Antarctica. It's the Australian icebreaker. The other thing you can think about might be a coccolithophore bloom. These are coccolithophores. They have calcareous plates that they plaster to the outside of their cell. They're photosynthetic. They're highly scattering, and you can see them from space. I have never swum in a coccolithophore bloom. Has anyone done that? It's definitely on my list of things to do. They do absorb. They are photosynthetic. They have pigments, so the water isn't quite white, but be worth testing out. Somebody said inorganic particles. So this is some image. These are some images from Lake Louise, where you have glacial lakes and glacial flowers. So glaciers flow over the continent and grind up rocks as they go into a very fine powder that are very small particles. And you can see how bright the lake is. Another place I would love to go and swim, even though it's going to be really cold. All right, so these are examples where we've considered the whole spectrum, but I think what's really important to realize is that, and this gets back to Eric's comment about the open ocean, that if you consider just narrow wave bands, just small parts of the spectrum, the ocean can act like a pure absorber, almost a pure absorber, or it can act like an almost pure scatterer. And so you can look in those wave bands and the ocean can either look black, there'll be no light coming out, or there will be tons of light coming out. Okay, and so I just, the near infrared and maybe in the UV are blue, right? And so that's where the open ocean may be in the blue, right? So I did a really quick download of some data from Giovanni, which is a data portal from NASA. This is the Gulf